Welcome to the course on two-dimensional signal processing, principles and practices. In this lecture, we'll look into the Hadamard transform, which is an interesting transform. Supposing the Hadamard transform kernel is called H. So like we had kernel matrix in DCT, DST and DFT. So this would also be having the kernel matrix H, which acts upon the signal 2D sequence or 1D sequence, and then we get back the transformed coefficients. So here the kernel matrix is called H, and this H matrix would contain +1 or -1 only, not any other values in the case of elements of the Hadamard. So n cross n matrix with elements +1 and -1, these are unique matrices. So here we have it doesn't require any multiplication because it has +1 and -1. So just directly we can, if you want to apply the Hadamard transform on any of the sequence, it is just having the 1 and -1. So you can just take those values only and take multiplication also will result in depends on -1, it would be minus, and it would be same value if it is +1. So it doesn't, in that sense, it doesn't require any kind of multiplication. And H into H transpose would result in n, the number, the size of it, and the identity matrix. Also, this matrix is orthonormal, which implies that its inner product is 0. So H I n, H j n, varying summation n to 1 to n, 0 for I not equal to j. So it has suppose an elements of H, capital H, are defined as H suffix ij. So then it would be valid for these cases. H I is not equal to j. Then what are the ways in which various Hadamard transforms can be obtained? So here is, if we have Hadamard matrix, that is always called side n. The side n implies that it's a rows or columns of n. It implies, the usual terminology used is not the size or row or column, it is side. Hadamard matrix is of side n. So n is the row or n is the column, we mean here. So then n can be 1 or 2, or it can be multiple of 4, and so on. So n can take value 1, 2, 4, and so on. So here if we have this Hadamard matrix as this, and then K is also Hadamard matrix if it is obtained from H in some of the ways actually. So what are the ways in which another matrix K can be obtained from H? So if we, by negating some or all the row elements, okay, so if we just negate it and get that matrix as K, that would also be Hadamard. And negating some or all columns of Hadamard matrix H, so then we can take that as a K, and that is also Hadamard. So that means negating either all the elements of the rows or the columns or some of the rows. If you take rows, some rows can be picked up or some columns can be picked up and negate it, and that can be combined to make another Hadamard transform. So and then permuting that rows and columns of also can give results in Hadamard matrix, that is K. So if you take this H of n, like the n is the suffix here, it is denoting the side 2 power n, where this n is again we say that elements, then H0, that n equal to 0 is have one. This is the matrix of H0, one element, that is 2 power 0, that is having only 1. And then here H1, if you take H1, that is 2 power 2 here, that has 4 elements. It doesn't show the value of the element. Of course, Hadamard matrix will have only ones and -1, that is +1 and -1. But Hn, when we write the size or the side, the n is, we call it as side is 2 power n. In that case, H0 will have only one element, and H1 that is equal to 2 power 1, or here is equal to that 2 power 0, that is 1, and 2 power 2 and 2 power 3, and so on. So here it will have 4 elements, and similarly H2 can be obtained from H1. So that is what we have is H1 represents as 4 elements, and H2, which represents 16 elements. H2 here, which can be obtained from 2 power to 4 into 16. So we can have it 2 power 4, which could result in H2, that is 16. So the matrix 16 elements which is having the 4 by 4 matrix, that n is going to be 4 by 4, the n is going to be 2 by 2, and so on. So H2 can be obtained from H1 in the fashion H1 multiplication or the Kronecker product into H1. So H1 Kronecker product H1 can result in H2. So what is this Kronecker product? How many elements will be there in the H2? So let's see, this H2 will have, I said there will be 8 and 16 elements at least it should have. So this H2 which you can see this is repeating H1 everywhere. So how do we obtain this H2? Is H1 Kronecker product H1, that means this 1 of this first element into 1 1 1 minus 1, this occupies the space, and then 1 into 1 1 1 minus 1, this is H1 again, the second element occupies the space. So the third one again 1 and 1 1 minus 1. So if we multiply this would be same. And the next one minus 1 here, minus 1 1 1 and 1 minus 1, that is H1. So this becomes minus 1 and minus 1 and minus plus. So this is the only element or the 4 elements which are different from the rest of the elements. This one element is different from other element. So when we multiply these two, so result in H2, which is having 16 elements, and that is called H2. So H0, H1 and H2. So Kronecker product implies this. So these four can be obtained through this. So supposing if we have a matrix A, just to explain this Kronecker product, M cross N matrix, and B is another matrix with PQ the size, and then so the product of A and B will have the resultant elements P times M and Q times N. Okay, so this is how we get H2. There are PM cross QN size. Okay, so then A Kronecker delta B, it's equal to, so A11, this first element of this, into the whole matrix of B, which is varying in the row of Q and in a column of P. So each here, that is here P11 B11 and up to Q, and this one is varying up to Q, and this one is varying up to P. So we have all of this, the whole matrix of B is this, okay, and multiply with the first element of A, and similarly all the elements of A will undergo this process of multiplying with B whole element. This continues up to A1n. So this is the first row, last element, and the total B, as we did in the case of the getting H2. So HM1 is the next, all the rows of it, A12 here, A11 and A21, and go up to AM1 into the matrix B, all the elements of this B matrix. And similarly the last element is AMN of the A matrix last element, and the whole matrix B needs to, and every element of it should be multiplied. Every element of it should be multiplied, resulting in the matrix size of this, and this would get expanded based on A also, A how many elements we have. So that's why the Kronecker product results in PM into QN size block of matrix. So the H1 Kronecker delta H1 results in H2, which has the PM and QN size 2 that is 2 cross 2 and 2 cross 2 matrices, results in that 4 cross 4 having the 16 elements. Here the product, for example, if to show that A Kronecker product B 1 2 3 4, this is one matrix A, suppose this matrix B, and how do we multiply it? 1 into this whole matrix 0, 5, 6, 7, and 2 into 0, 5, 6, 7, and similarly 3 into 0, 5, all the elements, and 4 into 0, 5, 6, 7, all of the elements. So we have this matrix now. So now if you multiply them, 1, 0, 1, 5, each element is multiplied, 1, 6, 1, 7, and similarly 2, 0, 2, 5, 2, 6, and 2, 7. That's 3, 0, 3, 5, 3, 6, and 3, 7, and similarly this. So we get this matrix here. So this is the matrix, the product of the Kronecker product of A and B. So which results in 2 by 2 matrices appended 4 times. That is, the four such matrices are combined in case of the product. Whereas this is different from the multiplication. N cross N or M cross N multiplied by P cross Q, that multiplication size would be different. Here is the block which we get is that from the Kronecker product. So this is how Hadamard transform is getting expanded. So Hadamard transform of a n cross 1 vector X. So it's a vector which has n rows and 1 column vector. So what is the transform? How do we get the transform of it? That is H into 1 by root n. This is actually the scaling factor. We use DCT and DST as well. So this is 1 by root n x into x, give you the transformed coefficients here V, and the H is the Hadamard matrix of side n, that is n here. So inverse can be obtained from this V. So V x equal to 1 by n H, if we make, that is giving x. So the inverse can be obtained. So for the case of 2D, if we extend that to 2D, n cross n matrix of X. X is the 2D signal and represented in a matrix form which has the n cross n size. Matrix size is n cross n here. So if, what is the Hadamard transform of it? So V, the transformed coefficient is 1 by n, that in H, this X is the signal and H transpose. So we get the transform coefficient as this, H transpose equal to H. So we can simplify this as Hx H 1 by n, like the DCT and the DST of the signals we had taken already. So this is V, and inverse transform can be obtained in similar fashion. X is 1 by n and HV is the transformed sequence now, are the coefficients, and HV and H we can get back the X. That is the same case in the separable form. Now, what are the properties, important properties of this Hadamard transform? As I said, it is interesting and having this unique matrices. So here, the kernel is here 1 by root n H. So that's the kernel which is real, symmetric, and orthonormal as well. So getting H is the one. If you know the H, then it is easy to get the transformed one. So this property is real and symmetric, also orthonormal. So it's a fast transform because it has ones and minus ones, and the n length vector can be computed with the order. You can see the order of computational complexity is n log base to n only. Its addition and subtractions result in computational reduction drastically, order n log base to n, if you use this for 1D. And then it has a good energy compaction property for most of the images, like the DST and DCT we had seen. So this is also used in the image processing for energy compaction property, and some of the other applications of Hadamard transform also we can use it, like especially in case of segmentation and etc. So now we take an example of the Hadamard transform, which for the size of X, the 2D image is only 2 by 2. It has 2, 3, 4, 2. These are the elements of the image matrix, or 2D sequence, we can say. Image and 2D matrix or the 2D signal, if we take only the N1 and the N2 would vary. So here what we say is that this is 0, 0, and then you have this is row and this are the columns. So the column indices N1 and N2 would change. So that's the only difference. Otherwise, we have this is now represented in the matrix form. Let's take the 2, 3, and 4, 2. The first row, second row, and first column and the second column in this fashion. So here n is 2. Both this is a square matrix. So we have n equal to 2. So normalized 2-point Hadamard transform. So first we need to know the kernel for any transform to be applied. So in the transform, to get the signal in the transform domain are the coefficients of the signal. The kernel needs to be for this 2 cross 2, that is n equal to 2, the Hadamard kernel is 1 1 1 minus 1. That's 1 by root 2 we got already in the previous. 1 by root n, this 1 1 1 minus 1, this is h. For this is normalized one, that's why you have this 1 by root 2 here. For 2, 1 by root n. So after getting this one, apply this v, the transformed coefficients to get it hx h transpose. So h transpose and h are same because of that properties, and v is hx h transpose now becomes h only. So multiply this hx and h, we get this like we did in the DST, discrete sign transform. The similar fashion we can do it, but here the simplification is that the kernels what you have is now to have only plus 1 and minus 1. It's very easy for the multiplication purpose also. 1 by root 2 is that, and h 1 1 1 minus 1, and we have this sequence x 2 3 4 2, which results in this row 6, and this row and column it is giving 5, and this one 2 minus 4, and 1 minus 1 and 3 2, multiplying it 1. So we get hx is this. Again multiply it with h, that's a simple way to do it. H is 1 by root 2, 1 1 1 minus 1. So the resulting v, the transformed domain and the image details are giving 1 by 2, and these details 11 by 2, 1 by 2, minus 1 by 2, and minus 3 by 2. So this is the result of the sequence what we had, and it's a 2D Hadamard transform. See that how easy to have this kernel to get the details of transform coefficients. Now taking the columns of H, that is what are the basis images, and can we get back the image from the transform coefficients. So here columns of H are, H we had 1 by root 2 1 1 1 1 by root 2 1 minus 1, that's what H of 0 and H of 1. So H had 1 by 2 1 1 1 minus 1, here you can see 1 1 minus 1, this H. So from that the column are taken. So now the column H, that is 1 1 1 and 1 by root 2, this is the H of 0, and H1 is 1 minus 1 H1. So this is only 2 columns, or we can take 2 rows as well. So to get the basis, like we did in the DST, so we can take the columns of the kernel, and then the basis images are obtained by Hij equal to Hi and Hj transpose. So the same way we did in the basis images for the DST. So here Hi and J are 0 0, in that case H0 and H0 transpose. H0 is this we had, and its transpose 1 by root 2 1 1. So we multiply this, get the basis image, for that is H of 0 0. That's the basis image which helps in getting back your original image from the transform coefficients. So this H00 is the one basis image. This image can be obtained in from other ways also in DCT and DST, that's from the basis functions. So here this is the basis image, and H01 it's 0 and H1 transpose. So H1 transpose is 1 by root 2 1 minus 1, and H of 0 is this. So here take this H0 and then this transform here. So we get this transform, and this multiplication result in 1 minus 1 and minus 1. So the next one H10, H1 and H0 transpose, H1 and H0 transpose. Yeah, multiplying them, getting 1 by 2 1 and minus 1 and minus 1. So we have the next basis function here, H11, H1 and H1 transpose. You can see the order in which it is written, that 1 1 0, the two of the columns are getting combined in different fashions. H1 transpose, 1 by root 2 1 minus 1 by root 2, and this is the transpose of the second column. So the multiplication results in it. So these basis functions or the basis images. If we get it's 0 0 0 1 1 0 1 1, and from this can we get the signal back. That in the DST we just stopped with the basis functions, and from that basis function in the similar fashion we can get that original x here. So how do we reconstruct it? So it's x is equal to summation I is varying from 0 to 1, j is varying from 0 to 1. This transform coefficients, that images what we got for Vij and Hij, this one. So 0 0 0 0, so we can take that element of V into H, and similarly V the corresponding elements 0 0 H 0 0. So we can expand it like that, H x into this is V 0 0 11 by 2. We got it here as 11 by 2 in the transformed case. 11 by 2, 1 by 2, minus 1 by 2 and minus 3 by 2. So taking this 1 by 1 in this case reconstruction, here is 11 by 2 and H 0 0, 1 by 2 H 0 1 and minus 1 by 2 H 1 0, minus 3 by 2 and H 1 1. So if you just multiply the corresponding positions Ij elements and then add them together, the summation of it x would result in, because H 0 0 is a matrix, isn't it? H 0 0 and H 0 1 is a matrix. So multiplying that would get, you can see 11 by 2, and this is a H 0 0 matrix, and this one V 0 1, V 1 0 and then V 1 1 and its corresponding H 1 1. So we get, this is going to be 1 by 2, 1 by 2, 1 by 2, 1 by 2, and multiplying by 11 by 2. This becomes 11 by 4, and the case, and adding this element again next, and this element subtracting, and this element, first element subtracting. So we get the first image x 0 0, and the next element, and here similarly this element comes back. This, all of them combining together would result in this point, and similarly the rest of the elements would be multiplied and getting back this as well, the fourth one. So the image what we get is 2 3 4 2, which we had taken already. So what we try to understand, so the signal x or the image which can be transformed, you get V, that coefficient, from the coefficients you can get back the sequence x through that x transpose, or if we have the we want to take the x and use the x and we get V. So if you know V and the kernel into V and V transpose, or kernel into V into kernel, so again get back to the sequence. So other ways to do the basis functions of the transform, either Hadamard transform or in the DST or DCT also, take them and multiply that with V and sum it over, so we can get the signal back also. This is how it helps in this basis images, helps in getting back this sequence again, 2 3 4 2. Now we take a little bigger image, the size 4 by 4. So 1 2, there is 4 3 and there are a few elements in it. So finding this basis images and finding the transform or the coefficients in using the Hadamard transform. So we'll see the applications of this real application in the future when we deal with this real-time images, and then we would, and the segmentation process, pointing line, extracting the line from an image and so on. This transform would be useful. So the Hadamard transform H for 4 by 4 matrix, you have to get the H 1 by 2, and this one we have seen that 16 elements H2, isn't it? So that H2 is you can see the H1 is repeating over here with it is obtained through the Kronecker product of H1 and H1, right? So that's what we had. This is H1 product of H1, right? So H1 is 1 1 1 1 minus 1. So that's what we get. Okay, so from this we got these elements, and 1 by 2 is obviously that's a normalized one, that's 1 by root 2. So we get these things, so 1 by 2 here. Now the for 4 by 4 of input image, then the kernel or the Hadamard matrices. Now we are going to multiply this in the fashion to get the transform coefficients. H in X into H transpose. So V is the H is symmetric, we have seen, so H transpose becomes H. So get this H and X is this one, and then again H we can multiply with it. So do the multiplication Hx, 1 by 2 corresponds to the H and H transpose here. So we get the final matrix 45 by 4 and 5 by 4 minus 7 by 4, 1 by 4, and multiplying this all the 3 matrices. In the left to right case, 1 by 4, 1 by 4 minus 11 by 4 minus 19 by 4, and we get this 4 by 4 matrix, which is the transform coefficient. So from these coefficients, again, can we get this basis images, and the basis images to get back X. Okay, so X can be obtained from the way in which also. So we will show that again. Just take the column of H, that is one column over here, this first column, second column, third column, and fourth column, H0, 1, 2 and 3. So we take this columns H0, H1 and then H2 and H3. So all have this 1 by 2 and now form the basis image. So basis images Hij, Hi and Hj transpose. So we get the 0, 0, H0, 0. So 1 by 4, this is the first row which is multiplied with the transpose, and it's 0, H0 transpose. So we get a 4 by 4 matrix again, 1 by 4 H0. This is one basis function. So H0, 1 again, make it H0 H1 transpose, and this is H0 H0 transpose. So getting H0 0 and H0 1, we have got this 4 by 4 matrix again. So from that here again H0 and H2 transpose. So H0 H3 transpose, H03. So it's not only these matrices, it has H10 because you have the 4 by 4 in that H1 and H0 transpose, that is second one, H11 here, H1 transpose, this is the next one, and we have more again H1 and H2 transpose, this one, and H1 and H3 transpose, getting the multiplication, as well the H2 and H0 transpose, and H2 and H1 transpose. Okay, so it doesn't stop here, even H2 and H2 transpose. So getting all of this and H3 transpose. So now from all this transpose, various ones, if you whatever you do, that you get is only the basis images will have +1 and -1. You can notice that in all the cases. Okay, so this is a unique, these are Hadamard matrices. So these matrices now we can combine even H3 and H0 transpose and H3 and H1 transpose. Okay, so this is 3 0 3 1 3 2 H3 and H2 transpose and H3 and H3 transpose. This is the total matrix, the basis image set is for the 4 by 4. It has we have to compute all of this basis images as the order increases, but the real complexity. But the thing is, you have only one and -1. So +1 and -1. So in that case, it is easy to. So how do we get back this sequence X? So X we get it through V00 H00, multiplying them, and V01 H01. So we got this is from the transformed coefficient, and these are all from the transform coefficients, and these are the basis images 0 0 0 1 0 2 and 0 3, and similarly 1 0 1 1 1 2 and 1 3, 2 0 2 1 2 2 and 2 3. So these are all the ways in which add it all of them together and get the original sequence, which is which we have. X is the big one, 4 by 4 image. This one 1 2 4 3 1 3 7 4. So if we multiply and add it together, so we get this X through the Hadamard transform, H1, all of them. So the resultant would be all the matrices, which has this is an example to show that result of the Hadamard transform. So what we had done is this Hadamard transform, how this can be used for the images. How do we compute the Hadamard transform for one-dimensional as well as 2D? So especially in 2D, it is very popular for certain applications. We'll do the application point of view of the Hadamard transform as we are doing the theory part of it. So the initially, and then we will apply these transforms to the images, real images. An example of 2x2 image and example of 4x4 image, and how the kernel varies for both the images. The kernel 2x2 you have to choose for the in the Hadamard, and kernel of saving the 4x4, that is side, not the size, we call it as side in the Hadamard literature for Hadamard transform. So we have the 2 and 4, that 16 element one, and then the 4 element matrices kernels have been used. So these transforms, DCT, DST, DFT, and then the Hadamard transforms are applied on the images to get some features, or to get some details of the images. For example, DFT is used in the case of frequency components, and DCT and DST are energy compaction properties. And this Hadamard also is very good energy compaction for most of the images, and used in line segmentation and extracting the line features from an image. So we would see that in the it's a unique transform, this Hadamard transform. Also it has especially +1 and -1 elements, and how to extract this Hadamard matrix from an Hadamard matrix by making some of the rows negating or some of the columns negating. We can get that also. And from the 2x2 Hadamard transform, how do we get this, the next H4 or the H2, which is having 4x4 Hadamard, the 16 element one, using a Kronecker product. So we learned that Kronecker product, how it's different from the matrix multiplication also. Thank you.